We've introduced the idea of both indefinite and definite integrals, and so far looked at what are some relatively simple integrals to evaluate using some of those basic formulas. For instance, the integral of e to the x is e to the x, and so on. In this section, we want to take a look at some more complicated integrals and look at our first integration technique, which is integration by substitution. So the first thing we need to pick up on is when it's appropriate to use this method. So substitution is going to be the method that we want to apply whenever we're trying to integrate composite functions. So we want to pick up on whether or not some portion of our function is a composite function. In this case, looking at these examples here, we have the integral of 7x plus 7, that quantity squared, times 7 dx. So in this case, 7x plus 7 is an interior function being plugged into something squared. So we have an interior function here, u equals 7x plus 7, meaning we have a composite function. What's left over is this 7 that we'll have to deal with, and we'll talk about what happens with that. But if we let u equal 7x plus 7, then we'll be able to rewrite this as the integral of u squared So instead of 7x plus 7 squared, we'll write it as the integral of u squared, which is much easier to evaluate. And then this 7 dx portion, we'll see in a second what happens to that, but that's going to end up getting replaced with du. So instead of dx, du. So that comes from the idea of taking the derivative of this substitution statement. So if u equals 7x plus 7, then du over dx, the derivative of this equation, is going to be 7. So this 7 is being used to replace that 7. Or I'm sorry, since this is the derivative of the substitution statement, we're going to be able to swap out that 7. And then in the end, we're going to have a problem where this changes from dx to du to change the variable that we're integrating with respect to. In our second example, we've got e to the 5x. So 5x is that interior function. So if we replace u with 5x, we'll be able to rewrite this integral as the integral of e to the u. And then again, we can look at the derivative of that substitution statement, which in this case would just be 5. So that 5 is going to be able to get swapped out, since we have the derivative of this statement being 5. So we're going to be able to write this as the integral of e to the u du. So each time, notice what we're ending up with is something that's much simpler to integrate. This original expression, in each case, is fairly complicated, but what we're ending up doing is rewriting a new expression that follows one of our simple integral patterns. In the third example, we've got 1 over something. So this is like 1 over x. So if we let, in this case, u equal 2 plus 5x squared, that's our interior function, and then consider the derivative of that substitution statement, we would get 10x squared. So we're going to be able to swap out the original denominator as well as this 10x. I'm sorry, that shouldn't be 10x squared. That should just be 10x. So we're going to be able to rewrite this as the integral of 1 over u du, which again fits our pattern for one of our simple integration formulas. This would just become the natural log of the absolute value of x. In our last example, we want to take a look at, but before we get into how we actually set up this integration process and then evaluate these integrals, we notice that we've got 3 plus t to the 6th being plugged into something to the 6th power. So that interior function is 3 plus t to the 6th. The derivative of that expression is going to be 6 t to the 5th. So this one, a problem like this, is going to end up being a slightly trickier substitution In each of the previous cases, we've taken the derivative of this expression we came up with for u, and whatever that derivative was, exactly matched some other part of our problem. In this case, this t to the fifth is only going to match part of our derivative statement. We're going to have this extra 6 left over. So we're going to have to look at how we end up working with that. But once we get through the steps and learn how to do this process of integration by substitution, we're going to end up being able to write this as the integral of u to the sixth du. And we'll have a little bit of extra work thrown in there because we still have to account for this 6. So something's going to have to happen with that. But so far what we want to do is just recognize this pattern, this general pattern of what we're doing. Identifying some interior function. Once we have that interior function, once we take its derivative, hopefully that's going to match up, or at least very closely match up, with some other portion, whatever is left in that integral statement. We're going to apply a process we haven't explained just yet, but be able to work this out so that we get a simplified integral statement, which then we can evaluate using the properties we've already established.